Right. Arthur's going to give the last talk in the session on a compositional theory of linearizability. Go ahead.
Yeah, so I will be talking about the compositional theory of linearizability. And, well, I first read Herlihy-Wing's original paper when I was in undergrad in a parallel computing class. And it solves this really important problem of how to specify a concurrent object. If we have a queue with an in-queue operation that takes a natural number and returns just if it was successful, and then a dequeue that, other than dequeuing, might also return a status for the queue if it's empty. In the sequential case, if someone calls dequeue, it's immediately that it just should return the empty queue because no one has called in-queue before. But in the concurrent setting, if someone calls dequeue, it could, of course, just return empty, but there could be also any number of in-queues in between that happen that make it undefined what that return to the queue is. So we need some other way of specifying these objects. What Herlihy-Wing propose is that if we take a concurrent trace like this, we can sort of detangle it and look at the total order per thread and find the operations that happen before each other, even across threads. And then those need to be preserved through a permutation to obtain a sequential trace. Now, we have two specifications, a concurrent specification, and then also an atomic one, which we know how to specify, and it's much simpler to work with, too. Now, what made linearizability become the gold standard of correctness so that I learned it in undergrad is that it has these nice properties, like locality, which says that if you take a bunch of linearizable objects, you can just put them together, and that thing is still linearizable. Or the observation, the equivalence with contextual refinement, which says that if you have one object that linearizes to another one, that's the case if and only if it, in fact, observationally refines that object, in the sense that if you take any program, the observable behaviors of that program running on top of the concurrent specification are all contained in the observable behaviors of the object running in the atomic one. What this all fails to tell you is, like, why linearizability? You know, I just started with this sequentially consistent model of computation, and somehow linearizability has these nice properties that do not really justify why you should use them from the axioms of computation. And even beyond that, the linearizability, when it appeared, it competed with other criteria, and it won because it had these properties, but there is no good explanation for why they do hold for linearizability. So in our paper, we present a new generalized definition of linearizability that is just not tied to atomicity. It is the first model of linearizability that harmoniously supports refinement, horizontal and vertical composition. We present a general, meaning category theoretic methodology for deriving linearizability from a model of concurrent computation with new, simpler proofs of locality and of this refinement property that benefit from that formulation. To show that this is actually effective, we have a program logic that is sound for this formalization, and we have some applications to compositional verification. Now, what do we mean by a compositional model? This is easier to see from the perspective of that application, where typically the approach we take to verify concurrent objects is that we first already know that some object observationally refines to an atomic object. So then we consider implementing some other object on top of that. And we know by the contextual refinement equivalence that the behaviors are included when you run the program over a simpler atomic specification. So now we're left proving another observational refinement. Now, suppose you're implementing a shared queue by just locking around every operation. So if you want to call an in queue, you import some sequential queues that you have in your underlying programming language. And then you acquire a lock, call in queue, receive the return, release the lock, and then return to that in queue. That is a Herlihy linearizable queue, but even though the lock that you use to implement it is also Herlihy-Wing linearizable, that queue has a race. It is just a sequential queue implementation. So if the threads actually use them concurrently, it will not work. So you can't use the locality property here to reason about these two objects together at the bottom, even though you are implementing a Herlihy-Wing linearizable thing. Moreover, there is not really an account of how this equivalence with observational refinement interacts with locality because they're expressed in different languages. Beyond that, the solution to this might be to inline the code of the queue as well as any modules that you might be using to implement that sequential queue too, so that you only rely on this lock. Now you can use all of the equipment you had before, but your implementation now inlines the sequential queue implementation, so this is not really compositional, because if you change that implementation, then you also have to change the proof of this refinement. Now, what if I also have a lock implementation that I want to connect with the shared queue? We already saw that inlining doesn't work, but beyond that, this lock might rely on some Herlihy linearizable object, like a fetch and increment object. Might rely on a counter with an even subtler specification than our racy sequential queue we had before, or even on a yield object, which is not even Herlihy-Wing linearizable. But beyond that, how do you connect these two pieces of code so that you, after verifying them independently somehow, you still get a verified object as a result? So what we want is something that supports refinement, vertical composition, locality, and linearizability, but for any sequentially consistent concurrent object instead. For that, we have this abstract construction or methodology where you start with some base model of computation that just has the basic axioms of your model. In this case, it's just a sequentially consistent model with some agents interacting with each other. And we also have a notion of refinement that works in this model. Now, it turns out that often in concurrent models, this doesn't immediately give you something that is really compositional. For that, you have to choose which programs will be the identity programs for composing programs. Once you make that choice, we can compute a new model that is actually compositional using this construction called the Karoubi envelope. So what we propose is a definition of linearizability that is abstract in the sense that it makes sense whenever you perform this construction, and we can show that it is equivalent to a concrete notion of linearizability that is familiar to everyone. And we also can give one extra axiom to get the refinement property. If we define a way to compose these objects together horizontally, we can also give more axioms to guarantee that locality holds. So in our paper, we use game semantics to construct a model of sequentially consistent concurrent computation. But all that you need to understand about it is that types correspond to games somehow, programs to things called strategies that go from A to B, meaning that they use objects of type A to implement objects of type B. And that object specifications corresponds to strategies from a certain unit game to A. Now, when we build our model of our game semantics model, we build it specifically so that those object specifications correspond precisely to the definition of a concurrent object that appears in Herlihy-Wing's classical paper. So you can just take that approximation whenever I say object here. So what does that model look like? We start by defining a sequential game model, which appears in the literature, is very traditional. And then we postulate some set of agent names. So with that, specifying a concurrent game just amounts to specifying the sequential game that all agents are playing together, like a counter game where all agents are sharing some counter. So a move looks like just a call or a return labeled by the agent that performs that move. And the set of plays of this game is just any sequentially consistent interleaving of valid plays of the sequential game they play. So a trace like this, which is what you would expect to see in even in Herlihy and Wing's paper, is precisely what we mean by a play of a concurrent game. So the benefit of using game semantics is that there is a well understood account of how you compose programs together. So it goes by this model of parallel composition plus hiding. But what matters is that you can take a strategy from A to B, a strategy from B to C, and compose it together into a strategy from A to C. You can think about that as even inlining. And we depict that as stacking two of these boxes, one on top of the other. Now, the problem in this concurrent setting is that even though this operation is associative, there is no identity element. And identity element here just means that if you pick a strategy from A to B and you compose with the identity on each side, it's just equal to the strategy you started with. In other words, this defines a model which has all the assumptions we want about computation, but unfortunately is not compositional. Now, what we meant before by having also a notion of refinement is, among other things, that if you have that the refinement holds about two strategies like so here, then and you compose them together, the refinement still holds after the composition. So composition is monotone with respect to refinement. Now, in the sequential setting, you do have an identity, which is given by this piece of code here, where to implement a queue, you import a queue, so that to call enqueue, you just call the enqueue of the underlying queue. So if you compose this with any code that implements a queue, it will still implement a queue. This is called the copycat strategy. One would expect that if you just pick the sequential copycat, parallel compose it together in a sequentially consistent way, that would be the identity. But it turns out that composition with the concurrent copycat can actually add more behaviors than you started with in your objects. So in this situation, we can observe that even though that's the case, the concurrent copycat kind of already behaves like the identity for itself, in the sense that it is idempotent. If you compose it with itself, you get back the concurrent copycat. That's all that is needed for you to perform this abstract construction here called the Karoubi envelope. And that what it will do is it will allow you to instead consider strategies that are saturated, that's the term we use for it, with respect to this concurrent copycat. So what that means is that if you sandwich the strategy between two concurrent copycats, then you get it back. So if we restrict to only strategies such that this property holds, then composition of those strategies is not only associative and has the identity. But in summary, these strategies here that are saturated, they are just able to either absorb or introduce this concurrent copycat interfaces, and they give a compositional model. So now we have two different worlds. We have a world where it's easy to specify things. We can specify objects that are, for instance, atomic, but also specify any sequentially consistent concurrent object, but it isn't compositional. So we really want our programs to live in this other world where you can actually compose them properly. There is a canonical way to convert a strategy from the non-compositional world to the compositional world by just sandwiching it together. And we call this operation a saturation operation, which we depict by K here. So now we want to know if we can actually use those specifications instead of specifying the objects directly in the compositional model. But this somehow has something to do with linearizability, so that's the point where we can give the definition of abstract linearizability. We say that an object implementation or a concurrent spec, VA prime, linearizes to its specification, VA, if it satisfies this refinement property, meaning that it refines to the saturation of its specification. Now, here we require that the implementation is saturated, but the specification does not need to be. And then the definition of a linearizable object is just a pair of this sort, a saturated strategy, a non-saturated, not necessarily saturated strategy, that satisfies this refinement property here. So why do we call this linearizability? It turns out, and this has been worked in a different setting on programming languages semantics, that the strategies are saturated if they are closed under a certain rewrite system over the place of these strategies. And what that means is just that if a play is in the strategy, and you can rewrite some other play into that play, then that play is also in the strategy. Now, what this rewrite system encodes is the notion of being more concurrent than some other trace while still having the same operations. What we show is that if you define linearizability the following way, saying that S is linearizable to T, if you can append some returns to it and then rewrite it into T with some extra calls at the end, then we will see that our notion of linearizability does correspond to linearizability. Now, it's important to say that here T does not need to be atomic, but if it is atomic, then this is equivalent to Herlihy-Wing linearizability. Moreover, if SO has every single pending invocation, meaning that T has no pending operations, then this corresponds to interval sequential linearizability. Now, this sequence SP we append is, of course, the returns that are usually added to pending operations of S, and the SO plays the role of the removal of whatever pending operations is left, even though we allow not all of them to be removed. And this rewrite precisely encodes the happens before order preservation that appears using partial orders in Herlihy-Wing, but using a rewrite system instead. So we are able to show that that saturation operation we saw earlier is equal to closing a strategy under all plays that linearize to some play already in the strategy. An immediate corollary is that we can express linearizability as that refinement property we saw before. So that justifies defining linearizability instead by that property. Now, we are able to show those extra refinement properties by simple algebraic reasoning. So for example, for the observational refinement property here, we want to show that if VA prime linearizes to VA, then running a program on top of them satisfies a refinement. So for the forward direction, we just start by putting the program on top of VA prime because we have the refinement by assumption here, and composition is monotonic. Then we are able to substitute it for VA with that copycat interface, but sigma is saturated, so it is able to absorb that concurrent copycat interface. And in reverse, we just instantiate the observational refinement with the concurrent copycat, which is a program like any other, and we note that the concurrent specification is actually saturated, so you can also absorb it there. For locality, you have to first say what it means to put two objects side by side. So what that means is that in our case, that we just pick all sequentially consistent interleavings of the two strategies you are joining together. So that turns out defines what is called a symmetric monoid, makes our model into a symmetric monoidal category, which just means it has a lot of nice properties you would expect from a product. But quite crucially, it means it interacts with the other structures we already have nicely. So for example, if you first compose strategies vertically, and then you tensor them together, that's the same thing as first tensoring them and then composing them vertically. If you compose the concurrent copycat with itself for a different type, then you just get the concurrent copycat for the product type. Because it also has to interact with refinement, it is also monotonic in the sense that if you have the refinement about the components, you also have it about their products. So at this point, we require one extra axiom to obtain locality, which is that this is actually an order isomorphism. So you can pick a product thing and project it back into its component somehow. And with that, we can show locality by just noticing that it can be restated using our formulation in this fashion, using the definition of abstract linearizability. And then by focusing on the right-hand side, we can apply functoriality twice. First, to split the concurrent copycat in two parts, and then to put the tensor on top. And after we do that, that's just the order isomorphism that is assumed. And that's the entire proof of locality. So this is in comparison with, for instance, the locality proof in the original paper, which goes by a sequence of nested contradictions arguing about partial orders. So we mentioned verification. And yeah, because everything sort of interacts well with each other, we're able to just refine the lock without having to refine that queue. And that helps you reason that the shared queue implementation never actually sees a trace of the queue that is not atomic. And for the lock implementation, we are able to linearize all of those specifications to simpler specifications. In the case of the counter and that yield object there, those specifications are actually still concurrent. They are just some kind of easier to work with shape for those traces, and show this refinement, which we do using a program logic. So we also define a program logic for verifying linearizability for this component. And well, it sounds with our notion of linearizability, so in particular with interval linearizability, and it directly connects with our compositional theory through this soundness theorem, which interprets as the strategies in this game model. So in the end, we have all of the tools to pick these two strategies that have been now verified, perhaps with a program logic, together into this large system that is automatically known to implement the shared queue correctly using the objects you use to implement the lock and the queue you're importing to start with. So in conclusion, we have these new foundations for linearizability, a compositional theory for it, with promising applications for compositional verification. I would suggest you check our paper for much more, and if you're adventurous enough, our TR, which has a concurrent game full description of this concurrent game semantics model, all the category theoretic formalization, a thorough comparison with previous work, and the example we describe in this talk, which we verify on paper using our program logic, and all the rules of the program logic with the proof of soundness, and actually much, much more that I couldn't talk here. So thank you.
All right, we have time for some questions.
Thank you. Pierre Clérambault from Marseille. So I think you know that there are lots of notions of concurrent games in the game semantics literature. So, I mean, do you know what your model, what would it relate to? I mean, I guess, do you know if it connects, maybe it would be a subcategory of the concurrent games model of Méliès and Mimram, perhaps?
Well, we use just sequential traces. So it is actually closer to the concurrent game model of Gika and Muraski, although it's not exactly the same. But we do have a thorough comparison with that one in our paper.
I think in Méliès and Mimram, they have traces, sequential traces as well. It's not, I'm not talking about event structures or anything like that.
Oh.
Yeah.
You mean the one on based on
But they don't have pointers, whereas Gika and Murawski have pointers, so it's a bit... but well, we can talk about that.
Yeah, okay.
Nice. Neil Krishnaswamy from Cambridge. So, in this Karoubi envelope construction, like you can basically choose any idempotent you want. So, and in this work, you chose the copycat. Does anything interesting happen if you choose a different?
Yeah, we are still thinking about choosing different ones. But what we do show in our paper is that there is a way to choose a strategy that corresponds to sort of an atomic copycat, in the sense that it's not sequential, but in the sense it has the agent names and so on. And then when you perform this whole construction using that atomic copycat, you obtain a model of concurrency that is atomic, and then you can prove that Herlihy-Wing linearizability arises from connecting this model with this copycat with a model with the atomic copycat. But that you will only find in our TR, I guess. Yeah.
Thank you.
All right, I think that concludes the session. Let's thank the speaker, and we have a break now.